Welcome to another delicious episode of Mother Nature's Kitchen. And here is your host, Chef Coriolis. Greetings and welcome to Mother Nature's Kitchen, where we're going to prepare another fantastic dish. Have you ever wondered, what could I prepare that would get the whole East Coast talking? I know I have. And when I think about affecting that many people, I need lots of water, wind, and excitement. And today's dish has all of those needs and more. We're going to prepare the perfect hurricane. Now, preparation is key in preparing the perfect hurricane. Now, critics have developed a ranking system for hurricanes as it's become a yearly global competition. Now the categories range through 1 through 5, 5 being the largest hurricanes, the closest to perfection. Now people often look at the ingredients for a hurricane and go, well, that's pretty simple to make. And that's the first mistake of most hurricane hobbyists. I'm going to walk you through the recipe to ensure that you understand the factors that are needed for each ingredient to create the perfect hurricane. Our first ingredient is the most important ingredient that needs the most preparation in order to create our hurricane, and that's energy. Energy is the fuel that builds storms into hurricanes, and we need a lot of energy to move water vapor from the oceans up into the atmosphere. Now, solar energy is the source of it all. Now, hurricanes can't directly use solar energy. They prefer thermal energy. So let me tell you a little bit about how solar energy is transformed into thermal energy. Well, water covers about 70% of the earth, and the solar energy is absorbed by that water all throughout the day. Hey, I just wanted to bring you down here for a closer look at the property of molecules called specific heat capacity. We mentioned it with warm ocean water. And I just wanted to give you a visual of what that property does for different molecules. So again, by definition, it means that it's the amount of energy an object or a molecule can absorb before it increases its temperature. So it has to absorb so much energy before it warms up 1 degree. Now, all different substances have different specific heat capacity values. We're going to compare two that are relative to hurricanes, water and dirt. Now, dirt is mostly made up of silicone, which is an element on the periodic table, and water is a molecule. And so we're just going to do some comparison here. Now, the specific heat capacity of silicone, which is in dirt, is 0.71 joules of energy per degree. Now, that's kind of like having a little container like this. And if energy was water, I would have to pour enough water in here, energy, to fill this up before it would increase its temperature by 1 degree. So it needs about that much energy. Not too shabby. Water, by comparison, needs this much energy before it can increase its temperature. Look at the difference. Specific heat capacity of water is 4.18. This is 0.71. This is almost 5 times larger heat capacity than silicone. So if I wanted to heat both of these up by 5 degrees, I would need to fill them up each 5 times, and the total amount of water I use to fill them up is the amount of energy I need. Now, if you had to fill both of these up 5 times, which one would you get a bigger pile of water out of? Water. And that's why water is very good at absorbing energy, which can be transferred into the hurricanes. Having a high specific heat capacity means that the water can absorb a lot of solar energy and store it as potential and thermal energy without increasing its temperature. And when I'm looking for the water with the most thermal energy stored up, I find that water near the equator. This brings us to our next ingredient, warm ocean water. Now, when I'm looking for the warmest ocean water to carry all of that energy that these hurricanes need to fuel themselves, I look for that water in the oceans near the equator. Why, you may ask? Well, down near the equator, there are advantages that allow it to absorb more solar energy than any other place in the oceans. First, it gets 12 hours of sunlight every day. Places like Ocean City, Maryland in the wintertime could get as little as 7, and in the summertime they could get more, like 14 or 15. Secondly, the sunlight that it receives in the equator is intense. And what I mean by intense is that the sun tracks so high it's almost straight over the ground. And that means that more solar energy is being absorbed per square inch, square foot of water. Now, places like, again, Ocean City, Maryland, the sun doesn't track as high in the sky, so the sunlight comes in angled. And just like a flashlight, if you bend the angle of the light, it spreads it out. So the same amount of energy, it's just spread out over a larger area, where near the equator, all that energy is concentrated in an intense, smaller area. Lastly, it's consistent. The seasons, the climate's not really affected by the seasons. They get 12 hours of daylight pretty much every day of the year, where our daylight varies. So those three factors combined give the oceans near the equator the ability to absorb the most solar energy, therefore having the most thermal energy to build these hurricanes. Low atmospheric pressure is the next ingredient we need in creating our perfect hurricane. It is crucial in moving the water vapor from the ocean surface up into the atmosphere, feeding energy and moisture into our hurricane. Atmospheric pressure is basically the result of all the air molecules in the atmosphere bouncing around and impacting you, and you're feeling that force. Now, air molecules don't carry much energy in them, so we don't even notice that impact in the pressure unless that pressure changes drastically. For example, flying in an airplane. Now, the higher you go in the atmosphere, the less air molecules are above you, pushing down, and it lowers the pressure. Now, the symptoms of that is you feel popping in your ears or pressure in your head and sinuses. Now, the lowest pressures in weather terms are results of warm air rising up and creating this upward motion and lowering the pressure, or winds that have an upwards kind of flow to them, again moving air molecules in the upwards direction, thus lowering the pressure. Here's a little demo to show you what I mean.
This is David. David is a latex glove filled with just regular atmospheric air. So, as you can see, when he's... Oh, careful, David. When you leave him alone, he just sets right there. The weight of the balloon, the latex keeps him grounded. Now I'm going to turn a fan on above David, and we're going to watch as I get him closer. Oh, he sticks to the top. Now you're like, oh, that's just the fan sucking David up to the top. That sucking motion that you're trying to describe is lower pressure. That fan is removing the air molecules from above David, allowing the air inside David to move in an upward direction. And that is the concept of low pressure. It allows that water vapor to easily rise. As soon as I get rid of that draft, David falls back down.
The lowest atmospheric pressures allow this warm water vapor to rise up and feed the hurricane. Now, this rising water vapor creates this column from the ocean all the way up to the top of the atmosphere called the stratosphere. And in some cases, when these hurricanes get strong, that upwards draft of warm air and moisture will impact the stratosphere and spread out and make that big canopy you see on hurricanes, the big circle. That force comes up. Now imagine that, a column of warm air pushing all the way up to the top of the stratosphere. That's a lot of energy. Now this column is not made out of wood or steel. This is made out of gases, air. And you can imagine that that's pretty hard to sustain. Now to add to that, this hurricane not only has to keep that vertical column above it to feed it, it also has to move across the ocean and the lands. Now, the last ingredient that we're actually going to try and minimize is wind shear. Wind shear could undo all of our preparations and rip apart our hurricane. Now, by definition, wind shear is when there's a small pocket of wind that is a different speed than the wind around it. And if we have too high of a wind shear, our hurricane, what will happen is the wind speeds at the top will be different than the wind speeds at the bottom near the ocean. And when that happens, your whole hurricane can topple over, and we don't want that. So, imagine you are balancing a heavy object on top of a stick in your hand, and you are walking along. Now, if you can keep that balance and you walk at a steady pace, you can keep that whole column stacked. But if you change your speed and slow down, your weight will fall over. Now, that's an example of high wind shear. Same thing happens to hurricanes. Now, there's two ways that high wind shear can happen. If the hurricane travels over land, that will slow it down at the surface because land's full of obstructions like hills and mountains. The other way it could slow down is if it intersects a big temperature change. So if the temperature changes, that will change the wind speeds. And again, a high wind shear will make our hurricane basically fall over and no longer be perfect. So we're going to put these ingredients together. Like I said, we're going to have the warm ocean water. There we go. Now we'll add in all of this solar energy. And here's our low pressure. Now here's a trick that I learned. We're going to sift out all the wind shear so that we minimize the wind shear. So I'm going to add the low pressure into the sifter. And we're going to work it all out. There we go. Oh, that's beautiful. And look at that. Whole big pile of wind shear was hiding in there. That's going to make our hurricane perfect. All right. So last thing we need to do is just put this in the oven for 3 to 4 days, bake at really warm temperatures, and we should get a perfect hurricane in no time.
We've baked our hurricane for 3 to 4 days. Now let's pop open the oven and see what we got. That's bread. What? The other oven? Alright, open the other oven. Let's see our hurricane. Oh, come on now, that's cookies. Can we get the right oven, please? Alright, I know we got it this time. This is our perfect hurricane. Oh, come on. Now that's casserole. You guys are just messing with me. Come on. Where's the hurricane? Alright, let's check this oven. And our beautiful hurricane. There it is. Excellent. Perfection.